Okay, now that we've discussed the trends in melting points and boiling points of substances, let's talk about some of the experimental setups that we use to exploit these differences in physical properties. And the first one we're going to talk about is distillation. And we'll start with simple distillation just to kind of set up the premise of how this works. The idea is simply that you have a solution, which is technically a mixture. And in simple distillation, the solute is a solid in its pure form, and it doesn't really have much of a volatility. In the best case scenario, it has no volatility, period. And so when you start heating up that solution, it's only the solvent that starts evaporating and exiting the flask. And what you can see here is a setup of such a such a design, right, in which you have your solution right here, which is going to be heated up with a burner, and then the vapor that is produced upon that process reaches this section which is called the condenser. And the condenser basically has inner walls which are hollow, and through those walls you pass cold water, and the cold water basically goes in through one end, out the other. And so the cold water basically is there to recondense the vapor that you've created from heating up the solution, and at the end you collect it in a separate flask. So start the process, start heating up this thing. Your, in this case, methanol molecules will start evaporating until they reach the condenser, at which point the gaseous methanol becomes liquid methanol again, and then it is collected on your flask. So this is the simple way of separating two molecules out of a mixture. But it does rely on the idea that the solute is non-volatile. Now, for a more physical description of what's happening to the boiling point, and even the vapor pressure of this liquid, Rolle's law is ideal for predicting this type of behavior. You determine and calculate the mole fraction of the solvent based on how much solid you have in it, and as long as you know the vapor pressure of the pure solvent, you can determine the vapor pressure of the solution. So this is something you've seen in general chemistry, but this is the actual setup for it. Okay, so very few cases where you actually have non-volatile solids present in here, and there is a different setup which issues when you have multiple volatile liquids present, and that is what we call fractional distillation. So here you have to add an additional piece of glassware that will allow you to separate the substances, because what happens is that in a mixture where both the solute and the solvent are volatile, when you heat up this mixture you're going to get both amounts in the gas phase. But this is the deal: if these two substances have different boiling points, it is possible to separate them, right? You will create a vapor pressure associated with both of them, but we're going to exploit the boiling points. And the way this kind of works, ultimately, you might remember these equations from Rolle's law, right? You get a vapor pressure, partial vapor pressure from one of the substances, you get another one from the second one, and you get your total vapor pressure for the combination of both. And the combined vapor pressure, if you look at the at, substituent A in this case, when all you have is that, the vapor pressure is going to be whatever the vapor pressure of the pure solvent is. But as you start increasing the amount of solute, this goes down, and at the point where you have all solute, which is no longer a mixture, by the point where you have all solute and no solvent, well, then this vapor pressure goes down to zero. But the same idea applies to the solute. If you start with just the pure solvent and you have no solute, then you just have the vapor pressure of the solvent. If you have all solute and no solvent, you just have the vapor pressure of the solute. But together they combined, right? So if you add the pink line with the blue line, you get this red line, which is the vapor pressure of the solution. And if you just have your simple distillation setup, that's basically the end of the story. But here's how you can manipulate it just in a way in which you can separate the two, and it's via this fragment here in this setup known as the fractional distillation column. So this looks a little bit more elegant than the simple distillation setup I showed you in the previous example. But the premise is almost the same. You're gonna have your mixture here at the bottom, which you're gonna separate, and this mixture is now composed of volatile solvent and volatile solute. So what ends up happening, and we'll take a look at the graph here as well, is that if you look at the temperature of the vapor as well as the temperature of the condensed vapor, so in other words, look at the boiling temperature of your gas mixture and the temperature of the condensation of the gas mixture, you actually create kind of a buffer zone that looks like this. The green line represents the boiling point temperature, and the blue line here represents the condensation line. And down here on the graph, what we're showing is the mole fractions of each one of the species. And so what you can see is that when the mole fraction of A is 1, that of B is 0. When the mole fraction of B is 1, that of A is 0. And then as long as they both add up to 1, this kind of works out pretty well. So 0.9 and 0.1, 0.6 and 0.4, and so on and so forth. Okay, so here we go. We're going to start with the premise that we have 90% A and 10% B, and they're both volatile. So what happens here is that you start heating up the mixture, and you heat it up until you reach the boiling point of the lower end of this buffer zone, right? So you reach the lower end, and when you reach that temperature, you end up heating up the mixture to evaporation. So here's where evaporation will take place, and you'll get some of these molecules to actually evaporate and start climbing up the column up here. Now, wherever this vertical line touches the lower boundary, you can look at the temperature and say, okay, that's the temperature, the initial temperature of the initial mixture that evaporated. But here is the deal. The evaporate has entered this column, and you might notice that this column has these spikes that point downwards. Those spikes serve as condensation points. They're cool enough and they don't heat up easily, so they remain kind of cool enough to recondensate that vapor you just created. But at the same time, you don't change the temperature a whole lot. So what happens is that in this graph, right, we start with a 90% A mixture. We take the vertical line until the lower limit. We read the temperature, but at the same time, notice that you're crossing this upper limit. And what you're really seeing here is that the lower limit is representing the evaporation of your solvent, and the upper limit is representing the recondensation of it. So by the time this condenses on one of these spikes, the liquid that is now being formed has been enriched in B. So you have lowered the content of A and you have increased the amount of B. And this is the beauty. The temperature doesn't necessarily change here. In fact, to reach the first spike, you had to have a certain initial temperature, T1, just to reach the first spike. So when this condenses and enriches the amount of B, notice what happens. The boiling point of that new mixture is actually lower than the original mixture that you started with. So you have more than enough heat present at these spikes to re-evaporate the newly enriched mixture of B. And so that's literally what happens. At T2, which is lower than T1, you end up re-evaporating the mixture and going further up the column until you reach the next set of spikes. And then this process of like evaporation, condensation happens ultimately until you have reached pure B at the top of the column. And then at the top of the column, you just have pure B reaching the condenser, right? So here comes the cold water, and there goes the cold water, You condense the hot gaseous methanol back into liquid, and then you collect it back into the receiving flasks up here. So this is kind of the beauty of this type of setup. You end up on the receiving end collecting always a substance with a lower boiling point, and you enrich it so long as you have enough spikes present in your condensation column, right? So here I'm just kind of showing you a zoomed in version of the condensation, the fractional distillation column, and you see the spikes right here where each one of those condensation events takes place, right? So initially you start with 90% A, you touch that spike, you recondense the liquid. In the process of the recondensation, you enrich the amount of B, which has a lower boiling point than originally the mixture had. So then that re-evaporates and goes up to the next spike, which then proceeds to recondense, enrich B, lower the boiling point, which then goes on to re-evaporate that mixture, and this goes on and on and on until you have pure B, right? And you just collect it. So it's a beautiful setup, and this type of glassware, by the way, um, this is something that glass blowers make all the time. And if you ever have a chance of taking a glass blowing class, I recommend it. It's kind of cool. It's really interesting. All right, now there are solutions where not only do you have volatile components for both the solute and the solution, excuse me, the solute and the solvent, but something interesting in that ends up happening. You end up creating something known as an azeotrope. And an azeotrope, in simple terms, is a mixture that, technically speaking, um, you can't necessarily purify completely. And if you look at the graph here, what you will notice is that our lower boundary, upper boundary buffer zone is actually composed of two segments, right? You have the left segment right here and the right segment, and there is a lower limit that connects the two together. Uh, Azeotropes are basically substances that will end up reaching a maximum or a minimum in the amount of content that you can have of substance A and substance B. But you don't necessarily separate them completely. So whereas in your regular distillation, your regular fractional distillation, you can get 100% A and 100% B. Here, you could potentially get um, pure A, but you will not get pure B. Or you could get pure B but not pure A, depending where you start on this diagram. So for instance, let's say that we start with 95% A and 5% B. We would start in this diagram and we basically do the same thing as we did before. We draw the vertical line up until the lower boundary. We draw the horizontal line up until the upper boundary. And then we bring it back down to the lower boundary, and we keep doing that until ultimately, as you can see here, you reach the lower limit, which is the 40% A and 60% B. And that's as much B as you're going to be able to get in this mixture. You cannot really get 100% B from this. But one thing to be said is that the component that is on the upper limit right here is technically what's present in your original heating flask. So in the heating flask, if you actually heat it up long enough, you could actually remove all of B from the original flask and collect pure B, perhaps at a loss, but collect pure A in the um, in the actual heating flask that you started with. But in the collection flasks, the most you're gonna get is 60% B, right? You will not be able to get from this particular setup pure B. On the other hand, right? So 40% A, 60% B. Now, on the other hand, if you start with a mixture that happens to be 95% B and 5% A, so you're actually here on the right side of the diagram, and you follow this approach, right? So you start at this particular temperature with the evaporation process, you condense, then you evaporate, condense, and so on and so forth, you will reach the same lower limit. But the difference here is that the molecule that has the greatest amount is B. So if you heat up the original flask long enough, and perhaps at a loss of yield, you can collect pure B on the boiling flask that you started with. But in the collection flask, the one that appears after your fractional condensation column is located, on the collection flask, once again, you will only be able to get 60% B for 40% A. So you really can't purify it any further than that on the collection flask, right? And this is kind of the aspect of azeotropes. Now, to be a little bit more concise about it, azeotropes are substances that tend to have um, different types of intermolecular forces. In some cases, they can be very drastic, like toluene, which is just a hydrocarbon no oxygens, no nitrogens. It's just carbon-carbon and carbon-hydrogen bonds in combination with water. This creates a positive azeotrope. Oh, and by the way, when you look at the azeotropes, positive, remember of positive or regular smiley face, right? That's positive attitude, positive azeotrope. But you have different types of intermolecular forces between these molecules. Hydrogen bonding for water, long dispersion for toluene. Same thing for benzene. Chloroform has a little bit of dipole forces, but still mostly non-polar. So these positive azeotropes, the reason why they're forming is due to the enthalpy of mixing these substances together. In particular, what happens is that the mere fact of mixing them is disrupting some of the hydrogen bonding interactions of the water away. And that ends up lowering the boiling point because you are kind of removing those highly and positively beneficial forces that water has at the expense of mixing it with toluene. So you lower the boiling point as a result of messing up some of the hydrogen bonding. But then on the other end of the spectrum, you have the negative azeotropes, which kind of do the opposite thing. And negative, think of upside down smiley, right? So it's sad smiley, negative. That's not good, right? But here you have an upper limit, and then you have lower limits on the extremes. And the opposite happens, right? So here you have to start somewhere closer to the middle because you're always going to go down. You are never going to go up in this cycle. It's always downwards that you go, right? So if you start with 45% A, you can follow the following trend, right? Vertical line, horizontal line, vertical line, horizontal line, vertical line, horizontal line. And ultimately what you're seeing in this negative azeotrope setup is that you will end up getting pure A. You'll get pure A at the end of this process on the collection flask. But if you end up heating up your heating flask long enough, the most you can get on the receiving flask, the heating flask, the original flask, the most you can get is 40% A in terms of purity, right? Here 100% A, here 40% A. And from this end, if you start on this end such that you're on the right side of this negative azeotrope graph, then you still go downwards, right? So this time we move towards the right until we reach the lower limit, which is pure B. So on the collection flask, we'll have pure B. But on the heating flask, if you heat it long enough, the most you're going to get is only 60% B, right? So this is an aspect of substances, in particular the ones that have by themselves strong forces already, strong intermolecular forces, but when you combine them they form even stronger. So in the case of acids added to water, you have hydrogen bonding in all of these setups by themselves, but when you add sulfuric acid to water you end up ionizing sulfuric acid, and so not only do you have hydrogen bonding, but now you have added ion dipole forces to the mixture, and so you have increased the intermolecular forces present in the mixture compared to the pure substances themselves, and in doing so you have increased the boiling point, and this is the reason why you have this upper limit in your negative azeotrope curve. So just something to be aware of. You'll probably see problems like this in the homework, so it'll be good to get familiar with them. Okay, in the next video, we'll talk about extractions. So I'll see you then.